Next is the fouling factor. After a water-cooled condenser has been in service for some time, its U value usually degrades somewhat because of the increased resistance to heat transfer on the water side due to fouling by the impurities and the water from the cooling tower. So the new condenser must therefore have a higher U value in anticipation of the reduction that will occur at service. So, baliktad. So, abang ka. The higher capacity with new equipment is provided by specifying a fouling factor 1 over H of FF meter squared Kelvin per watt. This term expands for the U value into 1 over U sub O is equal to 1 over H sub O plus X times E sub O over K over A sub M plus A sub O over H sub FF A sub I dahil sa water plus A sub O over A sub I A sub I. Several different agencies have established standard for the fouling factor to be used. One trade association specify 0.000176 meters squared Kelvin per watt, which means that the condenser should leave the factory with a 1 over U sub O value of 0.000176 A sub O over A sub I less than the minimum required to meet the coated capacity of the condenser. Yeah. This is the value of fouling factor. The superheating. So dito, makita niyo yan, the superheating. This is the temperature distribution in a condenser. Sa condenser, ito yung cooling fluid, yung water, normally ganyan, diba? Entering and leaving. Now, even when the refrigerant condenses at constant pressure, its temperature is constant only in the condensing portion. The constant pressure ito, pero sa temperature niya bumababa. So, because sa temperature bababa hanggang naging saturated, tapos yung cooling naman ganun din. So, because the vapor coming from the compressor is usually separated, the distribution of temperature will be as shown in figure 29. So, ano yung i-consider mo dito? So, because of the distortion in the temperature profile caused by the superheating process, the temperature difference between the refrigerant and the cooling fluid is no longer correctly represented by the LMTD. LMTD is equal to T sub C minus T sub I minus T sub C minus T sub O over ln of T sub C minus T sub I over T sub C minus T sub O. This is the cooling fluid T sub C. This is the inlet, T sub I, ito, condenser T sub C. Okay. Applicable lang to pag constant yung T sub C mo. But it is common practice to use equation 43 anyway with the following justification. Although the temperature difference between the refrigerant and the cooling fluid is higher in the separating section than calculated from equation 43, the convection coefficient in this section is normally lower than the condensing coefficient. The two errors compensate somewhat for each other, and the application of equation 43 along with the condensing coefficient over the intercondenser area usually provides reasonable accurate results. So pwede mo rin siyang gamitin with this justification. So this is na yung equation mo LMTD. So malilito ka, di ba? Mag-iisa-isa ka pa niya. Next, evaporator. In most refrigerating evaporator, the refrigerant boils in the tube and cools the fluid that passes over the outside of the tube. Evaporators that boil refrigerant in the tube are often called direct expansion evaporators. Yan. Nag-expand siya doon sa loob ng tubo. Yung sa labas, yung hangin or yung normally hangin to. So this is figure 30 shows air cooling evaporator. And figure 31 is the liquid cooler. Ito naman is water. Papasok niya. Tawag niya liquid cooler. Or chiller. Sa chiller kasi merong cooler, merong condenser. Ang cooler mo is also an evaporator. Boiling in shell. Siya. Dito, water mo, tama, nasa shell. Next is the boiling in shell. So ito, heat transfer niya meron din dito, di ba? So the classic prediction for heat transfer coefficient for full boiling of water at atmospheric pressure is shown in figure 32. So this to temperature and the Q over A. The tests were conducted by immersing heated wire in a container of water. In the boiling regime AB, the boiling is called nucleate boiling, okay, where bubbles form on the surface and rise to the pole. The equation of the curve is approximately Q over A is equal to C as delta T from 3 to 4. Ito lang, A to B. Where Q is equal to the rate of heat transfer, A, heat transfer area per meter, C, constant, delta T, difference in temperature between the metal and the boiling liquid. Boiling and shell, kung yung meron kasing natawag na sa ibang ano, sa shell yung evaporator, nasa shell yung refrigerant. Okay, meron doon. So ito na yun, boiling in shell. So to write the equation in another form, divide both sides by delta T. So Q over A delta T is equal to H of R is C times delta T from 2 to 3, where H of R is the boiling coefficient, watts per meter squared Kelvin. The value of H of R increases as the temperature difference increases, which physically are due to the greater agitation. The disturbances frees the bubbles of vapor from the metal surface sooner and allows the liquid to come into contact with the metal. So the rate of evaporation can increase to peak at point P, where so much vapor covers the metal surface that the liquid can no longer intimately contact with the metal. A further increase in temperature difference decreases the rate of heat transfer. So the graph in figure 32 is useful in predicting trends for heat transfer coefficient for boiling outside tube bundle. House Hoffman summarized the work of several investigators to provide the band shown in figure 33. Yung heat flux, yung Q over A, and this is the heat transfer coefficient. Ito yung pwede mo na gamitin itong range na band. Heat transfer coefficient for refrigerants 12 and 22 boiling outside of the tube. Hindi natin na-discuss yung mga types of evaporators. Okay? Sa refrigerant, pero kasi mga flooded type. Okay? So, boiling inside tube, so figure 34 shows local coefficient throughout tube for 3 different levels of temperature. So, heat transfer coefficient of refrigerant 22 boiling inside tube. So, evaporator, di ba, nag-evaporate siya. That is part of boiling. So, the heat transfer coefficient is highest for the high evaporating temperature, probably because at high evaporating temperature and pressures the vapor density is high, permitting because at high evaporating temperature and pressure, the vapor density is high, permitting a greater fraction of metal to be weighted with liquid. Pressure drop in tubes. The pressure of refrigerant drops as it flows to tube-type evaporators. The effect of pressure drop on system performance is that the compressor must pump from a lower suction pressure, which increases the power requirement. On the other hand, a high refrigerant velocity can be achieved if more pressure drop is permitted. And this high velocity improves the transfer coefficient. So, typical pressure drop for air conditioning evaporators are 15 to 30 kilopascals. So, linagay dito. Pero sa ibang book, sa heat exchanger designs, so meron tong mga equation. Diba? Tulad dun sa power plant natin. Meron siyang graph. Expansion devices. So, ito na yung the last of the basic elements in the vapor compression cycle after compressor, condenser, and evaporator is the expansion device. The purpose of the expansion device is twofold. It must reduce the pressure of the liquid refrigerant and it must regulate the flow of refrigerant to the evaporator. Okay? So maraming kasi ito. Maraming types. So hindi natin na dito. Capillary tube. Instead na pag maliit, gamitin mo capillary tube instead ng expansion devices. The capillary tube serves almost all small refrigerant systems in each application extend up to refrigerating capacities of the order of 10 kilowatts. A refrigerant tube is 1 to 6 meter long with an inside diameter generally from 0.5 to 0.2 millimeter. So makita niyo malilit na aircon, wala siyang expansion valve devices, kundi capillary tube, yung nakakoil lang na tubo. The name is misnomer since the ball is too large to permit capillary action. So yan, sinabi niya. Liquid refrigerant enters the capillary tube and as it flows through the tube, the pressure drops because of friction and acceleration of the refrigerant. Some of the liquid flushes into vapor as the refrigerant flows through the tube. Next, selection of capillary tube. The designer of a new refrigeration unit employing a capillary tube must select the bore and length of the tube so that the compressor and tube fix a balance point at the desired evaporating temperature. Final adjustment of the length is most often cut and dry. A longer tube than desired is first installed in the system with the probable result that the balance point will occur to a too low an evaporating temperature. The tube is shortened until the desired balance is reached. So, cut and dry. So, graphical method of capillary tube selection. So, graphs to facilitate selection of capillary tubes are based on the data by Hopkins and revised with data by Wittisell. So, ito yan. The first graph, figure 35, presents the refrigerant flow rate as a function of entering pressure at the capillary tube for a tube that is 1.63 mm in diameter and 2.03 meter long. So, yan. Inlet pressure, tapos ano yung flow rate sa cooling. So, the various curve in period 36 represent performance at variety of inlet conditions. The various curves in figure 36 represent performance at a variety of inlet conditions of subcooling and fraction of vapor. This is the correction factor to be applied in figure 13.13.7. Ibig sabihin yan yung figure 35 natin for other diameter and length of capillary tube. So that is the combined graph of figure 35 is the one in figure 36 for presenting correction factor to the flow rate of figure 35 for other lengths in diameter. So pag mag-select kayo ng capillary tube, so ito yung dalawa lang mo. Next, constant pressure expansion valve. So the constant pressure expansion valve maintains a constant pressure at the outlet, the entrance to the evaporator. It senses the evaporator pressure, and when that pressure drops below the control point, the valve opens wider. When the evaporator pressure rises above the control point, the valve partially closes. Okay? So float valve. The float valve is a type of expansion valve which maintains the liquid at constant level. Kaya float. In a vessel or an evaporator. So yung plus tank sa power plant. A float switch which opens completely when the liquid level drops below the control point and closes when the level reaches the control point will give the same net performance as a modulating type of float control. Next, superheat controlled thermostatic expansion valve. So, ito na yung TX. Nakalagay, di ba? TEB. Ang symbol niya. So, the most popular type of expansion device for moderate size refrigeration system is the superheated control valve, usually called a thermostatic expansion valve. The name may be misleading because control is accreted not by the temperature in the evaporator, but the magnitude of superheat of the suction gas leaving the evaporator. So, yan. Control siya ng superheat. The superheat expansion valve regulates the rate of flow of liquid refrigerant in proportion to the rate of evaporation in the evaporator. So, figure 37 is a photograph of thermostatic expansion valve. Yes. Next, the manufacturer's rating to thermostatic expansion valves. Kanya-kanya yan. So the catalog of manufacturers of expansion valve usually show the refrigerating capacity associated with the flow rate of which the valve is capable. So in order to provide some reserve capacity, most manufacturers show the refrigerating capacity at perhaps 75% of the full flow of the valve. The flow rate through the valve is a function of pressure difference across the valve, and the velocity through the fully open valve can be computed from the hydraulic formula. So the velocity is equal to C times square root of 2 times the pressure difference in meter per second, where C is an experimentally determined constant and the pressure difference is in kilopascal. Although the refrigerant following the throttling process in the valve is a mixture of vapor and liquid. Equation 44 applies to liquid because the vaporization doesn't occur until after the fluid has passed through the valve. The liquid is momentarily in a metastable condition. Sample number 10. So the catalog of an expansion valve manufacturer specifies a refrigerating capacity of 45 kilowatt for a certain valve when the pressure difference across the valve is 500 kilopascal. So the catalog rating apply when vapor-free liquid at 37.8 C enters the expansion valve and the evaporator temperature is 4.4 C. What is the expected rating of the valve when the pressure difference across it is 1 to kilopascal? Given the refrigerating capacity is 45 kilowatt, pressure difference 500 kVA at 37.8 C entering expansion valve, evaporator temperature is 4.4 C. Required expected rating when the pressure difference is 1 to kilopascal. So solution, velocity is equal to C times the square root of 2 times pressure difference in meter per second, with all other data as constant except for pressure difference and refrigerating capacity. So the refrigerating capacity is proportional to the square root of 2 times the pressure difference. So then the new refrigerating capacity is equal to 45 kilowatt times the square root of 1 2 over 500 is 69.7 kilowatt. Okay. So this is now the new rating of the valve when the pressure difference is 1 2. Laki nga. Kaya lang yung pressure difference mo, malaki rin. So this is the end of this topic.